What's going on, everybody? In this video, we're going to be doing part 2 of our Algebra 2 final review. Now, originally, I was going to do the last 25 practice problems in this video. However, I decided that was going to take much too long, and so what I'm going to do in this video is just kind of split that up and do half, and then I'll make a part 3 video where I do the other half. So without further ado, let's get into the topics that we will be discussing in this video. So, in this video, we'll be doing the first 4 topics here, okay? And then the Part 3 video will have the other 4 topics. Okay, so we'll be doing complex numbers, polynomials, which, that's basically like end behavior, things like that. We'll be talking about different things with polynomials that you talk about in Algebra 2, right? End behavior being, I think, the one that most people struggle with. We'll also be getting into rational functions and equations, right? That's when you have like a polynomial over a polynomial, so you have like a fraction, right? And so those are really tough. And then we'll talk about long division and remainder theorem. And the thing about remainder theorem, a lot of students have struggle with it because they just don't see like how it makes any sense, how that actually comes to be. So I want to definitely touch on that in this video and then do plenty of practice problems with it. Okay, so with that being said, let's hop in to our first topic. And actually, before that, I do want to note, definitely try each problem on your own first, right? I want this to help you as much as possible, and I think that's a great way for me to be able to do that. If you try each problem on your own first, you know exactly where you're going to be struggling with that problem, and so you can then watch my walkthrough and figure that out, right? And once I help you get over that little hump, you can maybe keep going and see how far you can get, right? And you can check your answers with mine, so try to just make this video work for you as much as you can. Okay, so let's get into that first question. And this first question is on complex numbers, and it's to simplify 5i to the 16 plus 3i to the 23 plus I to the 26 into a plus bi form. Okay, so how do we actually go about tackling something like this, right? When we have i's to, big powers like this. Okay, well, one thing that you need to know is that I think most of you have used this circle, right? Where you have your different remainders that you can have. You might say like 1, 2, 3, 4, and you'll have I, -1, -I, and 1, right? And so maybe that'll look familiar, but the main idea is that I is the square root of -1, right? And so, well, how do you know what I squared is? Well, I squared would just be I times I, right? And we know that I is the square root of -1, so it's like multiplying the square root of -1 by the square root of -1. And when you do something like that, the square root goes away, and you're just left with -1, right? And so, what about I cubed, right? What would happen there? Well, for I cubed, you will, and I can take this. Guys, let me know in the comments if you like it better like this or if you like it better with the lines. I think for now I'm going to do it without. Anyways, for I cubed, you are just going to be, multiplying I squared by I, right? That would give you I cubed. And so we know that I squared is -1, and I is the square root of -1, right? Or we could just leave that as I, right? And so we get that I cubed is -I, right? And then I to the 4th, you could just think of that as being I squared times I squared, and I squared we just found was -1. And so we multiply that together, and we get that I to the 4th power is 1. Right, and so that lines up with this circle over here. Okay? And to be honest, how I remembered this, like, I didn't try to go through and do that the entire time in Algebra 2. What I ended up doing was I kind of made a little jingle in my head. So I would think I -1, -I, 1. Now that's really cringy, but it helped me remember it, right? And actually, as a little tip, it's often that the most cringy things will actually be the things that you remember, So there's a little tip. Anyways, coming back to this, how does this help us find what these things are? Right? Well, let's think about it. Let's think about I to the 16 power. For I to the 16 power, we can divide this up into I to the 4th, I to the 4th, I to the 4th, and I to the 4th. Right? If you add up all those exponents, you get I to the 16. Right? And so what was I to the 4th? Well, it was 1. And so we end up just getting, 1 times 1 times 1 times 1. Right? And of course, that's just 1. So we know that I to the 16th is also 1. Now, how you could have also figured that out is, well, what's the remainder when you divide 16 by 4? Right? If you divide 16 by 4, you get 4. And that 16 goes away. And so you have 0 as your remainder. And that's why when I draw this circle, I actually like to put this as 0, right? Because then it'll illustrate, what you have left over when you, like as a remainder, what will you have left over, okay? And so 5I to the 16, right? If we know that I to the 16 is 1, we can just write 5I to the 16 as 5. Okay, and I'll make space for that down here. Okay, so we'll be writing our final product down here. Now, if we wanted to do I to the 23, right, that's the next thing on our list, we can divide by 4 again, right? Because this will be the same thing as breaking I to the 23 up. We'll erase this for a second, and we'll do the same exact tactic for I to the 23, right? Well, we can just have a bunch of I to the 4ths again, just like we did last time, right? This will give us 16, this will give us 20, and then what do we have left over? That's exactly what dividing is asking us, right? Because if you combine all these, you get I to the 20th, okay? But we want I to the 23, so we need an I to the 3rd power, right? And so hopefully you see now how these are all 1s, and then this is what's left over. And so I to the 23 is equal to I to the 3rd power. Right? And that's why we care so much about that remainder. When we actually divide 23 by 4, let's do that, right? 4 can go in 5 times. And so when it does, you get 3 as your remainder. Okay? And so that tells you that you'll have an I to the 3rd left over when you're finished taking out I to the 4ths. That's exactly what this whole thing tells you. And I just want, I'm sorry I'm going over this in so much detail, but really, I just want you to understand where this all comes from. Okay, because when I was in Algebra 2, I did not understand any of where this was coming from. I kind of just tried to remember it in my head rather than actually understand it. Okay, so if I to the 23rd is the same thing as I cubed, well, what is I cubed? We said that was negative I. Okay, and so negative I, if you just substitute that in for here, you would get a negative 3i, right? Or you would get a 3 times negative I. Right? And you could rewrite that as a minus 3i. Okay, let's do our last piece here. We have I to the 26th power. Okay, let's do the same thing again. We just divide 26 by 4 to see what the I is that we have left over. Okay, and so if we divide 4 by 26, well, that will go in 6 times, right? And then we subtract 24. We have 2 left over. Okay, and 2, since 2 is our remainder, right, well, we're going to have an I squared left over. And so I squared, that's negative 1. Okay, and so I to the 26th, right, that just ends up being negative 1, right? Because what this has showed us now, just as a quick review, is that I to the 26th is equal to I squared. Okay, for this reason. And I squared is negative 1. So we have a minus 1. And simplifying this, we can combine like terms here. 5 minus 1 is 4. And you get 4 minus 3i. Oops. All right, there you go. There's your answer. All right. So moving right along here, let's express the following in a plus bi form, right? This is going to involve a lot of multiplication, right? Because we're going to have to do some, we used to call this foiling. I don't know if you guys still call this foiling, but multiplying two binomials out, and then we're going to have to do it here as well, right? Because we want to get this all expanded, combine like terms to get that into a plus bi form. Okay, so let's go ahead and try this, right? Let's start by multiplying this 8 times the 3, right? That gives us 24. Then we can multiply the 8 by 2i. That would give us 16i. Multiply the 5i by 3 to get a 15i. And multiply the 5i by 2i to get a plus 10i squared. Okay? And let's do the next one. We have minus, and make sure that you realize that you're going to have to distribute this negative eventually. Okay, so what I'll have coming after this will just all be in brackets. We'll have the 4 times the 4, that's 16. We'll have the 4 times the negative I, that gives us negative 4i. A I times 4, 4i, and a I times a negative I, which gives us negative I squared. Okay, now let's do just a little bit of simplifying, right? Let's simplify this piece and let's simplify this piece. When we simplify the first piece, we get, well, 24 plus 31i, right? That's what this ends up being. And then we get plus 10i squared. But I squared, we know, is negative 1. And so really we can write this as 14 plus 31i. Now if you're like, hold up, where did that come from? Well, this piece is negative 10. And so you just do 24 minus 10, that gives you 14. Okay, and so let's simplify the other side now. Well, if we know that, well, actually, let's write this out. We know that the middle pieces will go away, right? We have a negative 4i plus 4i, and negative I squared, well, what is that going to become? Well, let's write that as negative what I squared is. Negative I squared is negative 1. Okay, and so this ends up being minus a 16 plus 1. Right? Negative and negative, you just make those both positive. Okay? And so you get 14 plus 31i minus a 17. And 14 minus 17 is negative 3. And so that's how you get your answer. Okay? So you get negative 3 plus 31i. Okay, now I want you to notice one other thing here, and this is actually going to be important. You might end up getting some questions on this. Okay, so that's why I want to cover this before we move on to our next problem. Okay, for these two binomials on this side, right, we saw that the middle terms canceled out. Right, and that's really nice because what ended up happening is, well, this thing ended up simplifying to something completely real, right? As in it didn't have any imaginaries in it. Okay? That's important. But why is that important, right? Like why am I underlining this right now? Well, when we get something real, right? If we get something real off of that, that ends up being something that we can describe in real life, right? Real life doesn't have any, imaginary numbers like, oh, how many items do you have over there? Oh, I have 2i. No, nobody says that, right? And so, and this is like a bunch of physics that you'll learn later on, that ends up being really important. And so what ends up happening in class is that you stress what these two things are, right? And that's their conjugates, right? That's how you'll end up getting a real answer, is you'll multiply two conjugates. Right? What does it mean to be conjugates of each other? Well, it means that you have a plus I before, right? And now you're going to just change that imaginary part to be negative. Okay? So it's the same thing. And what ends up happening when you do that is you get, well, a plus 4i, and you get a minus 4i, and they cancel, and you get a real answer. Okay? So conjugates are really important. Okay, and that's why they get stressed in Algebra 2. moving on to our next problem. We want to see which of the following parabolas does not cross the x-axis. Okay? So, for this problem, I lost my voice for a little bit there. The idea is like we could position a parabola to where it isn't crossing the x-axis anymore. Let me show you an example. A quick example is just something like this. Here's our xy axes. This messed up. And we could have a parabola like sitting like that, right? And it's like, okay, well, what are the zeros of this? Right? Because it doesn't end up crossing this x-axis. And so what you end up finding is that these zeros, like if you set this parabola, let's say it's x squared plus 5x minus 3, right? If you have something like this, okay, and you end up setting it equal to 0 to find where x is 0, you end up getting that x is equal to, you know, let's say like 3 plus or minus I or whatever, right? You end up getting an imaginary answer. Okay? And so if the parabola doesn't touch the x-axis, you will get imaginary zeros. Okay? And that's the whole point of this problem. Okay? When we ask which of the following parabolas does not cross the x-axis, we're really asking which of the following zeros, or you know, which parabola has imaginary zeros. Okay? And so, how do we figure out whether that is going to be true, you know, without having to go through and do quadratic formula a million times? Well, we can use this thing called the discriminant. Okay, you may have heard of it before, and I'll show you where it comes from. The quadratic formula states that x is equal to negative b plus or minus the square root of b squared minus a 4ac all over 2a. Right? Hopefully you know that. Okay? Now, where's the only place? Just look at this and tell me, where's the only place that you could get an imaginary answer here? What would have to happen? Well, hopefully you would tell me that the only time you can get an imaginary is when you get a negative under a radical, right? And, well, so we can see that the only way that can happen is if b squared minus 4ac is less than 0. Right? If it's less than 0, it could be like -1, -2, and so that would give you an imaginary answer. Okay, that would give you imaginary zeros, therefore the parabola would not cross the x-axis. So, keeping on this point, right, this b squared minus 4ac is extremely important, right? This b squared minus 4ac is called the discriminant, right? It's what will determine if your parabola will have imaginary zeros, if it'll have real zeros, right? It'll talk all about that. And so I'm going to underline this. Okay? Very important. So what we're going to do, all we have to do for these problems, we don't have to put each one of them into the quadratic formula, right? All we have to do is just use the discriminant and see if it's less than 0. Okay? So hopefully that makes sense. Let's start out with A. Okay? A is 2x squared plus 5x minus 3. Okay? If we use the quadratic formula for this, right, or you know, it would be a lot. Okay, there's your short answer. It would be a lot of work. So we use the discriminant, we use b squared minus 4ac, and we see that b here is 5, and so we have a 5 squared. Then we get a minus 4 times a, which is 2, and c, which is -3. Okay, and so now we're just going to say what 5 squared is, that's 25. And we get plus because there's a negative here, those will make a positive, and that's just going to be 8 times 3 is 24. Okay, and so 24 plus 25 is 49, and that is not less than 0. And so for this, we're going to get real zeros. Okay, and that means the parabola will cross the x-axis. Okay, now let's try B, okay, because obviously A is not our answer. Okay, we get a 4x squared minus 4x plus 5. Well, let's use the discriminant again. We get that b squared minus 4ac is going to be, our b is negative 4. We square that. We then subtract a 4 times a, which is 4, times c, which is 5. And that gives us a negative 4 squared is 16. Then we have a 4 times 4 here is 16. 16 times 5 is, well, guys, here's a little trick. If you want to do 16 times 5 in your head, do 16 times 10. That's 160, right? You just add the 0 to the 16. And then just half that. And if you half that, you get 16 times 5. Right? It's just like dividing by 2 on both sides, because 10 divided by 2 is 5, so you get this thing. And so if you divide this by 2, you get 80. And that's the quick way that I do that in my head. Okay, so here you can see that this is definitely less than 0, right? We have a minus 80 here, and we only have a positive 16. And so what ends up happening is, well, you're going to get imaginary zeros. Okay, and again, think about that. In the quadratic formula, this piece would end up being negative, and so you have a negative under the radical. And so when you do the quadratic formula, you end up getting i's. All right, and so b is going to be our answer here. B is not going to cross the x-axis because it has imaginary zeros. All right, so that is it for our red section. If you want to take a quick 5-minute break, feel free to. All right, and we can just come back when you're done. Okay, so assuming that you've taken that break, let's move on to the orange section on polynomials. Okay, so starting off with this problem, we're asked if the point negative 4, 5 lies on the graph of a power function, we'll define what that is in a second, with an even exponent, name a point other than the origin that must also lie on this graph. Okay, so if you looked at this problem, right, you might just be like, whoa, you might stop at the word power function and be like, what the heck is that thing? Okay, because it's hard to memorize all these different terms. Okay, and I get that personally. Like, I hate doing that. It happens definitely in Algebra 2. And so here's what a power function is. A power function is literally just a x to the b power, right? Or just something of that form. What are things that take that form? Well, if you have like a polynomial, like 2x squared plus 5x plus 3, right, which is like something we had in the last example, right? This has a bunch of little power functions in it, right? You could describe, 2x squared is of this form, 5x is of this form, and if you say that 3 is 3 times x to the 0 power, right, it's also of this form. Okay, and so that's what a power function is. And so the idea here, right, because a power function is just one of these, okay, and so we have a power function with an even exponent. So that's saying that b is even. Okay, so we'll just outline the key information here. We have a power function with an even exponent. Name a point other than the origin, so we don't want the origin here, right? Because you can see hopefully that this thing will cross through the origin because it doesn't have any like y-intercept out here. So you can think of that y-intercept as being plus 0. Okay. And so there's another point that must lie on this graph. Okay. So starting out with the point negative 4, 5. We know that that's a point, so let's just graph that quick. Okay, 1, 2, 3, 4. And we're going up 5, right? Yeah. 1, 2, 3, 4, 5. So we know that that point is on our graph. Now, here's what you got to know about power functions, right? There are 4 main, like, different looking power functions, right? The ones that you'll see, and you'll see variations off of, right, is when you have something to an even exponent, like x squared, x to the 4th, x to the 6th, right? They'll all look like this, okay? They'll all look like this. And hopefully you can like kind of see the whole effect if hopefully my camera is not blocking out too much of my hands, right? And if you put a negative in front of those, if you have like a negative x squared or a negative x to the fourth or a negative x to the sixth, they'll look like this, okay? And if you have an x cubed or an x to the fifth, right, you have an odd exponent, the graph will, well, I'm not sure. Let me draw it because I don't want to go the wrong way with the camera. X cubed just looks like this, right? Or x to the, like x to the fifth will all have that same like look to it, okay? And then if you do like a negative x to the third or negative x to the fifth, it'll go that way, okay? But here we know that b is even, right? And so we're dealing with an x squared or an x to the fourth, right? This thing is even. And so what that tells us is that, well, we know that this graph will either look like this or this, right? It's got to be one of the two. And since we know that we have a point up here, right? And, since we know the y-intercept of this, right, it's 0, right? Any power function, right, it is going to, by itself, is going to have a y-intercept of 0, okay? Now, you know that it's a parabola that looks like this, right? And because, it has to pass through the y-axis here. So you have 2 points, and you kind of just connect it with a parabola, right? And so if you understand that, hopefully it should make sense to you what you know another point on the graph is, right? Since this power on this power function, right, it's even, we know that we're dealing with an even function, right? That means it has symmetry about the y-axis. What that means is that not only do we know that this is a point, but we also know that this is a point. Okay, and what's this point? Well, it would be, instead of negative 4, 5, it would be 4, 5. And that, my friends, is our answer. Okay, hopefully that explanation wasn't too, hopefully that wasn't too confusing. I didn't want it to be, but yeah, it's a lot to deal with here, right? And if that was confusing to you, I think we'll fine-tune that in the next few problems, okay? Because we'll be talking about end behavior a lot more. And so maybe that'll help you understand this. Okay? So that was our answer, right? That was another point that we know that was on the parabola. But here is question 30. And so this problem asks, find the zeros of the quartic function, y equals x to the fourth power minus x squared plus 4. Sketch this graph as well. So we want to be doing that. Okay. Now, you might look at this, right, and be like, what is going on with this x to the fourth power, right? Like, like if I saw a parabola that looked like that, I would freak out. But what you actually have to realize here, right, since we have an x to the fourth and an x squared, it actually kind of looks like a quadratic, right? Here, let me show you what I mean. If we said let u equal x squared, right, we could say that this quartic function, right, quartic means to the fourth power, right, and quadratic means that you have an x squared in there. But we could say that this new quartic function is, well, if u is x squared, that means that u squared is x to the fourth power, right? And so the x to the fourth power right here is just going to be u squared. And then we get minus 5 x squared is u, and get plus 4, right? And so this is a quadratic, okay? And you can just factor this, all right? The idea is, what is two numbers? I like to draw a little x graph here. What are two numbers that add to be negative 5 and multiply to be 4? Well, hopefully you would see that that would be negative 1 and negative 4. Okay? And so you end up getting that a u minus 1 and a u minus 4. Okay? And so now that we have this, right, all we have to do is just substitute back in for our x squared. We get that y equals x squared minus 1 and x squared minus 4. Okay? And so hopefully you see how it factors in the same way as a quadratic, right? And it makes it even more apparent when you put that u in there, right? Because you have, something squared minus something to the first power minus something like a constant, okay? And so you can actually just factor the the x to the x to the fourth, like the quartic function, in the same way that you factor in a regular quadratic. Now, let me be careful when I say that, though, because if you had something like an x to the third in here, or an x power, right, and you also had that in your function, it wouldn't work, okay? Because the whole idea is that, you know, these things are like evenly spaced, right? Like you have an x to the fourth and then an x squared, and then you can think of this as being x to the 0, right? So they're all even powers, okay? And so hopefully that all makes sense. Now, we can continue expanding this, right, using difference of two perfect squares, right? And just so everybody's on the same page, okay, this is the only time we'll go over this. What a perfect square is, right? An example of a perfect square is something like x squared, okay? Because if you square root it, you get something nice. Another example of a perfect square is 9, because if you square root it, you get something nice. And a non-example of a perfect square is something like 18, right? Because if you square root 18, you don't get something nice, right? And so I think you get, what, 3 rad 2, right? Because this is the square root of 9, the square root of 2, and that's 3. Yes, you get 3 rad 2, right? So you can't eliminate the radical, and so 18 is not a perfect square, okay? And so that's the whole idea. So with that definition, you can hopefully see how this is a difference, right? You have a minus sign there, of two perfect squares. Okay, that's what this means. When you say difference of two perfect squares, that's what you're talking about. And I did not know that until I was in, like, I don't know, I didn't really understand that fully until I was in probably like calc, honestly. You know, it was something I should have known when I was in the class that you guys are in right now, but I didn't, you know? So with that being said, when you have a difference of two perfect squares, hopefully you remember that you can just factor it like this, right? That's the first one, and then we'll do the second one. X minus 2, x plus 2. Oh, sorry. Is that right? Let me make sure I did this right. Yes, I did. Okay, yeah. Because you would get a x squared minus 2x plus 2x. And then you get a minus 4. Right, sorry, I kind of messed that up in my notes, so. Alright, we're set. So, knowing that this is going to be our fully factored form, the only thing left to do in this problem is just sketch this graph. Okay? We just sketch it. And we can actually do that pretty easily. Mark out our graph. Okay? And maybe it'll help to get some graph paper on here, so I'll just switch the paper type up quick. Okay? And that also tells me that this line wasn't even straight to begin with. Alright, and we'll mark this point as being x equals 1. This point is x equals 2. This will be x equals negative 1. This will be x equals negative 2. Okay? Just to make the graph even. So we have 1, 2, negative 1, and this should have been negative 2. Okay? And we know that this graph passes through the x-axis at all these points. Right? How do we know that? We'll set this equal to 0. Right? That's how you'd originally find your zeros. And you would see that, you know, what can make this equation true? Well, if x equals 1, x equals negative 1, x equals 2, and so on and so forth. Right? And so we know that this graph crosses the x-axis at all those points. That's why it's nice to have something in factored form. Okay? Now here's the deal with this graph, right? What kind of end behavior is it going to have, right? Because if we know the end behavior, right, we know how it looks, right? How does it, you know, then we'll know like how to actually graph this. We'll know where to start, right? Because yeah, cool, we know where it crosses the x-axis, but how does it like actually travel through them? Okay? So here we started out with a x to the 4th power, right? Let me show you. Right? Our function was this. right? And when we look at end behavior, we just want to look at the biggest power of x, right, which is that x to the fourth. Okay, we also want to look at the fact that it's positive and not negative, right? We don't have a negative out front. And so what that tells us is that since it's a x to the fourth power, it's like this. Okay, so it needs to start at infinity and end at infinity. Okay, that's important. So we know that we want to start at infinity, right? We want to cross the x-axis here. We want to cross the x-axis here, cross it, and then go back up to infinity. Okay, and that, my friends, is your graph, right? And so we can write that as being, we can label the graph as y equals x to the fourth. What was it? Plus or minus 5x squared plus 4. Okay, so yeah, and in my graph is kind of sloppy, right? My handwriting needs to be a little bit better at times. But hopefully you see there, right? It starts at infinity, it ends at infinity. That's what we want. Okay, so let's take the graph paper away now, and we'll move on to our next problem. Okay, now this is kind of the same idea as question 30. We want to create an equation for the following graph in polynomial form, right? So now we're given this graph, right? And we want to get from here to here. Okay, let's see if we can do it. So starting off here, we know that this graph, first off, starts at infinity and ends at infinity, right? And when I say that, I mean like in the y direction, right? It starts from y equals infinity and it ends at y equals infinity. Okay, so if we want to create this equation, we need to realize that it's the highest power of x is going to have to be even. So it's going to have to be y equals, let's say, x to the fourth, and then a bunch of other stuff that is, you know, like x cubed, x squared, whatever. Okay, and so that's where we need, that's a good starting point, right? So we can write down starts at infinity and ends at infinity. Okay, and so we see it crosses the x-axis at -3. It crosses the x-axis at x equals 0, and it also it doesn't cross. So we're gonna have to make a note of that, right? But it touches the x-axis at x equals 4. Okay, so if we just put this in the same form as it was above, right, we would want to do y equals x plus 3, right? We wouldn't want to do minus 3 because I'll show you why in a second. We'd want to do an x, right? Because you could write it as like x plus 0 if you wanted to, right? And that's just x. And then we have a x minus 4. Now, why did I switch the signs here? Well, think about it. If you're trying to find your zeros, right, you set this thing equal to 0, and then what values of x will give you 0, right? What values of x will your graph cross? Well, what things can make this thing 0? X equals -3 can, and so, you know, that's because that's the value, right? That crosses the x-axis, right? Not the value that you write down here. The value that you write down here is supposed to kind of counteract this, right? And make it 0. That's why we switch the sign, because that's not our 0. Our 0 is coming from here. So hopefully that was kind of a little aha moment. It was for me when I first noticed it. But here's the problem with what we have written out so far, right? There's only one more thing that we have to do, and that's realize that, well, we had something not cross the x-axis, right? It kind of just like kissed it, right? It just kind of kissed the x-axis and it kept going. That means something. And what that means is that we have to square that part, okay? Or we have to just take it to some even power, okay? So if we square this, then we'll end up getting, you know, we'll end up getting like an x to the even power, okay? And, you know, out of this entire thing. Let me show you what I mean by that. if we distribute this, like the biggest x term can be given by multiplying all of these pieces, right? And yeah, that's an x cubed, but this is being squared. So we'd actually have our largest term be x to the fourth, right? And so that's good because, and when we distribute the rest of this out, we just get a bunch of nonsense here. Okay? And so the reason why that's so good, and let me just erase all this and just write x to the fourth. The reason why this is so good is because, well, now we have something, x to the fourth is something that starts at infinity and ends at infinity, right? Because it has an even power. And also, now we have something that will kiss the x-axis. But you may be confused as to, why I put the square in here. And so I probably should explain that. Okay, I want to explain that in a little more detail. If you don't want that detail, you can just head on to the next problem. Okay, and so let's think about it. If we have let's talk about y equals x, right? If we just have y equals x, that's just a line, right? And that crosses through the x-axis at x equals 0. But if we have a y equals x squared, we get something a little bit different, right? We get this graph. Okay? And that just kisses the x-axis. Now what about y equals x cubed, right? Well, that looks like this, right? Or something like it, right? And that crosses through the x-axis. But y equals x to the fourth? No, that one, that just basically does the same thing. It kind of just ends up being like a little flatter, I think, right? And so that is what ends up happening to x to the fourth, right? It kisses the x-axis. And so hopefully you can see a common theme here. Everything with all these power functions, remember that term from before, all these power functions with odd exponents, right? You can think of this as being x to the first power, we have an x to the third power, right? All of these things are going to cross through the x-axis, but these things are just going to kiss it. And so if you want a term to just kiss the x-axis, you need to put it to an even power, okay? And here we could just, square it. That's the best bet. Just end up squaring it. That's going to be your even power, okay? But if the only time that you wouldn't put a square here, and I'm sure that's something that you've wondered about too, like when would I put a 4? When would I put a 6? Well, if it tells you that if you have a problem that's okay, well the highest power of this polynomial is x to the 10. Well, then you know that you would have to put you'd have to put an 8 here, right? Because it would need to be even, right? But it would also need to match like this, because the highest power you get out of here is x to the 8. The highest power you get here, that's just an x, and then you get an x. And so when you multiply those together, you get an x to the 10. And so that's the only way that you can get an x to the 10 out of this polynomial as your highest power. Okay, so hopefully that makes sense as to why we do all that. I know that, that doesn't really get explained too much. I mean, you might get it explained to you when you start off in class, but it might be really easy to just zone out and not try to take that in or get really confused. So hopefully this explanation helped. But anyways, this right here is going to be your answer. Okay? So, question 32 asks us to describe the end behavior of the following polynomial. Okay? This one should just be a breeze. If we've already talked about 31, we've already talked about the end behavior and the two things that it relies on. Right? We want to talk about where is the highest power of x. Well, it's right here, right? The negative 5x to the fifth. Okay? And there are two things that we want to key in on for end behavior. The first thing is the highest power even or odd. Right? If the highest power is even, we know the graph is going to look like one of these things. I can't even twist my arms that way. Yeah, if it goes like this, it's going to have a even exponent, right? But if it goes like this, right, we know that it has a odd exponent. So that's why the highest power matters. Okay? But how do we know if it does look like this or this, right? What's the differentiator? Well, that's if it's negative, right? So that's the second thing that we want to key in on. Is the highest power, or is the, maybe you'll get what I mean if I just write it like this, hopefully. Is the highest power negative? Or if I write this like a little more mathematically correct, is the highest powered term negative, right? That's how you would correctly write this. Okay? The idea being, it does this thing have a negative in front of it. That's really how you can, simplify saying that. So those are the two things that we want to check, right? And if we check these two things, we'll know whether the graph looks like this. My screen is kind of bugging out here, guys. 1 second. There we are. Sorry about that. But anyway, so what I was saying was, depending on these two things, we'll know whether the graph looks like this, this, or this. Okay? That's the things that we're trying to figure out. So, looking at y equals negative 5x to the 5th power, right? Is this power even or odd? Well, it's odd, right? It's an odd number. And so we know that the graph either looks like this or this. Now, it's negative, right? That's the second thing that we check. And so that means that instead of the graph looking like a y equals x cubed or y equals x to the 5th, right? It's going to end up looking like this, right? It's going to end up looking like y equals negative x cubed or y equals negative x to the 5th. Okay? And so this is what our graph is going to look like. Okay? And so we've narrowed it down to this looking thing. Now, if we put this on a xy axis, okay, you should be able to get an idea. Like, this isn't exactly what this graph looks like, right? It might have like a bunch of bumps in here and do all sorts of things, right? That obviously was not a good representation. It would look something, I don't know. just graph it and you'll see what I mean. But the whole point is that it's still going to have the same end behavior, right? And so if we just use the end behavior of this, it's going to be the same as the end behavior of this. So how do we write the end behavior? Well, we'll say as x approaches negative infinity, right? Meaning as we go this way, what happens to our y? Well, our y goes off into infinity, right? And then as x approaches positive infinity, right? As x goes this way, what happens to our y? Well, our y goes downward, right? And so y is going to approach negative infinity. And that, my friends, is your answer. Okay, so there you go. First two sections are, I believe, complete. And yeah, now we're going to move on to rational functions. So again, if you want to take a 5-minute break, feel free to do so, and then we will get right back into this. Okay, so assuming you've done that, let's hop into our second to last section for this video. So for rational functions, right, before I even get into this problem, let's talk about what a rational function actually is, because you might not know. Okay, a rational function is a polynomial over a polynomial, right? So you could have something, exactly, like this is a rational function, right? You have a polynomial over a polynomial. Okay, so if you want to write that like generally, like with like, variables and stuff, you could say that the general form of a rational function is this, where p of x and q of x are polynomials. Okay? That's what a rational function is. Okay? And so there's a couple key components with rational functions, right? And you could be talking about asymptotes, which I think is more of a pre-calc thing. That's something I'll talk about then. But for us, we generally just want to look at the domain, right? We want to look at, is this thing going to be fully continuous? And generally the answer is no, right? This is not going to be continuous because, there'll be gaps. Like it might look like this, right? Why? Because this denominator could be 0, right? And so if that denominator is 0, well, then we get like a 3 over 0 or like a 5 over 0, and we can't have something over 0. Okay, and so that would take away from our domain. So how do we find where this thing is 0? Well, it's literally just the same thing as we've always done, right? We have something like this. You can try to factor it, or you can just use quadratic formula. And for that, let's write down the formula again. Let's sing it together. X is equal to negative b plus or minus. Okay, I'm not singing it. I don't want to sing it. It would just take too much self-confidence to do that. But anyways, b, right? B is going to be negative 1 here. We can actually write that out if you want. A is going to be 2, B is going to be negative 1, and then C is going to be negative 10. Okay, and so negative b is 1 plus or minus the square root of b squared is negative 1 squared minus a4 times a, which is 2, times c, which is negative 10. And that'll be all over 2a, which is 2 times 2. Okay, let's do a little bit of simplifying here. We're going to get x equals a 1 plus or minus the square root of, we have a negative 1 squared is 1, minus, actually this will be a plus because we have a negative and a negative. And so we get plus a 4 times 2 is 8. 8 times 10 is 80. Right? And by the way, this is a really nice way to write your radicals. Do this at first, and then just write down what your radical is, and then you know how far to extend this. That was something cool that I found out when I was in physics, I think. Anywho, back to helping you with your final. Yeah, you can just put this over 4 because 2 times 2 is 4. Okay? And so here you get 1 plus or minus the square root of 81 over 4. We know that the square root of 81 is 9, and so you get 1 plus or minus 9 over 4. Okay? And so continuing on here, we get that x is equal to 1 plus 9 over 4, and x is equal to 1 minus 9 over 4. Okay? And 1 plus 9 over 4, that is equal to 10 over 4, which, if you divide that by 2 over 2, is equal to 5 over 2. Okay, so that's one of your x's. And this one, 1 minus 9 over 4, is equal to negative 8 over 4. Divide that by 2 over 2 again. Or, I guess you could divide that by 4 over 4. And you just get negative 2. Right, negative 8 divided by 4 is negative 2. Okay, and so you get that your two x's are going to be 5/2 and negative 2. Okay, and so those are the only points on this entire graph where you're going to get a discontinuous function, right? Where you're not going to actually get a value. You're not going to get a value because you have a 0 in the denominator. Okay, so we need to account for that in our domain, and we're going to write that in interval notation. Okay, so let's just do a quick review of interval notation, and then we'll write down our answer. Okay, for interval notation, a bracket means you include an endpoint. A parentheses means you don't include an endpoint. Right? You definitely never include infinity, right? And, for these points right here, we don't want to include them because they're not in our domain, right? They're not in our list of x values. And so, if we want to write our domain here, let's start from negative infinity and see where we make our first stop. Well, negative 2 will come before 5 halves, right? And so we'll stop at negative 2. And we won't include it because negative 2 is not included in our domain. We're going to put a union, right? We're including another point, right, in our domain. And that's going to be starting at negative 2 and going to 5 halves. And that's going to be in union with starting at 5 halves and ending in infinity. And then there you go. That's your domain. Okay, so hopefully that makes sense, right? And of course, remember the domain is all of your x values, right? It's all the x values where you're going to get an actual y, right? Where you're going to get an output. Okay, so assuming that makes sense, let's move on to our next problem. And that next problem is to write the following fraction in simplest form. Well, you have y squared minus x squared over 5x minus 5y. Now, this problem, hopefully, if you remember the whole difference of two perfect squares story from before, right? Hopefully you can see that this is difference of two perfect squares, right? And so if you want to just, write that like it kind of looks like a 25 minus x squared, right? Or something like that, where you have two perfect squares. Okay, and you're taking the difference of them. So if we wanted to do that, we'd write this as, 5 minus x and 5 plus x. Right, and I know that looks a little backwards from what you're used to, but what you're used to is x squared minus 25. And in that case, you'd write it as x minus 5, x plus 5. Right, so it just gets flipped around when you have the perfect squares in different order. Okay? And so how would we write this thing? Well, it would just be y minus x, y plus x. All right? And then let's just do the denominator. Here we can just factor out a 5, right? We have a 5 in each of these pieces, so let's factor it out. We get 5 times x minus y. Okay? Now, here's the thing. You might see this and you might get really frustrated, right? We have a y minus x right here and a x minus y right here. These are basically the exact same thing, right? But one of them is flipped. So how do we flip them so we can cancel them out? Well, it's actually pretty simple. Let's factor out a negative. Okay, let's factor out a negative out of the denominator. Okay, we can rewrite this as y minus x, y plus x. I did not have enough room to write that there. Let me just move that here. And then we'll put over a negative 5. And if we factor out a negative here, we'll make the x negative, make the y positive. And so we'll get negative x plus y, which we can rewrite as a negative 5 times a y minus x, right? That's just a commutative property. So now we have that these things cancel off, and we're left with our answer of, we can bring that negative outside of the fraction and write our answer as y plus x over 5. Okay? And that is our answer. Okay? So, you just gotta be comfortable with, messing around with things, right? Like, you see the difference in two perfect squares. You gotta realize that, even when there's letters there, right? When there's letters, it can get confusing, and I'm sure I would have got confused in the same place when I was in Algebra 2. So just be on the lookout for that. And also, if you have things that look really close, you can probably try manipulating them a little bit. Factor out a negative, do something like that. Okay? Let's move on to our next problem. On problem 35, we want to solve for x, and here we have something disgusting. Okay? Well, we have like a lot of x's, we have fractions everywhere, and so how do we even start off with something like this? Well, we want to, whenever you're faced with a problem like this, find common denominators. Okay? That's the first part. Okay, and then what you're going to find when you have your common denominators, right, is that you can drop the denominator completely. Okay, I'll show you why that is in a second. And once you've dropped that denominator and you're just kind of focused on this piece, right, since you're going to have to be multiplying by other x's, you're probably going to end up with a quadratic. And so what you're going to want to do is get this into like some kind of quadratic form, right? So you're going to want to get this into like a ax squared plus bx plus c form, right? And hopefully, I mean, you should always end up with a quadratic. Maybe sometimes you won't. Maybe sometimes it'll just be like something linear, or maybe sometimes you'll have like a cube term in there. In which case, maybe you'd have to use grouping, which is another thing you can review. But yeah, that's the idea. You want to get it into like a quadratic form, right? And have it equal to 0, and then you just use quadratic formula, or you just factor, right? Something like that. And I'll write or there instead of like an and, right? So that there's a bunch of different things you can do, but that's the general step-by-step process. Okay, and so let's see what our common denominator is going to be here. Okay, well, and to give me more room, like as much room as possible, I'm just going to shrink this down a little bit. Okay, so let's do step 1. Let's find common denominators. Okay, in this case, what's our common denominators going to be? Well, you see that we have an x minus 1 here and here, and we also have an x, right? And so maybe we could multiply this piece by x over x, and this piece by x over x, and this piece by x minus 1 over x minus 1, and get a x times x minus 1 as our denominator, right? You kind of just want to multiply all of them together. That's kind of how it goes. Like you just want, you have an x, you have an x minus 1, so your common denominator is x times x minus 1. So let's go ahead and do that. We first are going to multiply this piece by a x over x. We'll multiply the x plus 5 over x piece by a x minus 1 over x minus 1. And we'll multiply this piece, the 3x plus 1 over x minus 1, times a x over x. Okay? And remember here, these are just the same thing, right? We're multiplying by 1. Okay? Every time we do this, we're multiplying by 1. And multiplying by 1 can actually help a lot, right? You can do different things with that 1, right? You can, if you have x minus 1 over x minus 1, you can use each of those x minus 1s in a different way, right? And that's why it's actually useful to multiply by 1. Okay? So let's actually, show what this is. So you get a x times x plus 3 over a x times x minus 1, right? Just writing this a little neater. X minus 5, x plus 5, x minus 1 over a x times x minus 1. Then you get a 3x plus 1 times x all over a x minus 1. And I apologize here. I've been writing these as plus signs. These are equals, I believe, right? Right. Sorry. Okay, I'll have to make note of that and edit that out later and just like give you guys a reminder of what I'm doing. So now that we have this, we can do step 2. We can drop the denominator. Here's why. Because the denominator really isn't doing anything for us anymore, right? If the denominator is equal all throughout, we can just kind of multiply it away, right? And what I mean by that is we can multiply each side by x times x minus 1, right? And multiply this side by x times x minus 1, right? If we distribute this one out, it'll just cancel off the denominators. And if we multiply this here, it'll cancel off that denominator. And when you cancel out those denominators, all you're left with is those numerators, right? X times x plus 3 plus a x plus 5 times x minus 1. And that's equal to a x times 3x plus 1. Okay, now we just distribute and we're going to end up with something in a quadratic form. All right, and so that's going to give us x squared plus a 3x, right? And then this piece is going to be x squared plus 5x minus a x, and then minus 5. And then we get 3x squared plus x on this side. Okay? And so let's just kind of start combining like terms on each side, and then we'll, subtract these over. So on this side we have an x squared and an x squared. That gives us 2x squared. We have a 3x and a 5x and a negative x. That will give us, 3 plus 5 is 8. Then we have a minus 1x, and that's going to be 7x. And then we have a minus 5 right here. Okay? And if we have this, still equal to 3x squared plus x, I'd rather us have to deal with a positive x squared. So actually what I'm going to do is I'm going to subtract all this over. Okay? And you'll see how, here we're going to get a positive x squared. So that's nicer. Okay? So when we do this, we get that 0 is equal to 3x squared minus 2x squared is x squared. X minus 7x is negative 6x. And then we have a plus 5. Okay? And from here, we're just going to factor. Right? We're going to factor and get that the two things that add to be negative 6 and multiply to be 5 are going to be negative 1 and negative 5. Right? Okay? And so we get that x equals 1 and x equals 5. But before we, circle this answer and call it good, we have some things in the denominator here. Okay? So we want to make sure that, our solutions are actually solutions, right? They don't give us a 0 in the denominator. So I think it'd be good for this problem, just to check. Okay, if you have a regular quadratic, you probably don't have to check. But if you have a square root, you could end up with extraneous solutions. If you have a fraction, you could end up with, having a 0 in the denominator. So you got to be careful. Right? So let's check 1, and actually to do that, I'm just going to copy this and bring it down. Okay, and sorry, I'm running out of room here a little bit. But when we plug in a 1, you can see that we're going to get a 0 in these denominators, right? And so 1 can't be a solution. Okay, when we plug in 1, we get a 0 in the denominator. So I think the other thing to do, let's just plug in 5 and see what we get. Okay, so this thing will become 5 plus 3, which is 8. So I guess I'll just write that here. Right, I'm taking that from here, and I'm just going to go left to right. We get 8 over 5 minus 1 in the denominator, right? And that's going to give us 4. Then we have a x plus 5. That's going to be 5 plus 5. That gives us 10. And then the denominator is x, which is 5. And that gives us a 3x, which is going to be 3 times 5, 15. Plus 1 is 16. And then we have x minus 1. That's 5 minus 1, and that's 4. Okay? And that gives us 2 plus 2 equals 4. And I think we all know, hopefully, that that is right. Okay? And so 5 is going to be a solution for this equation, whereas 1 will not be. And so 5 we can circle as being our answer. All right? Moving on to our next section. If we want to take a break, this is our last section here. I think we have 3 problems on long division, and then that's going to be it for this video. All right? So let's get into this. So we want to express 2x squared plus 15x plus 20 all divided by x plus 6 into quotient remainder form. Okay? Now with a problem like this, the idea is that we're just going to go through and do some long division. Okay? And we're going to write this in quotient plus remainder over divisor form. Right? That's what quotient remainder form is. Okay, why does this form make sense? Well, if we think about how we like long divide regularly, let's pick two numbers that don't divide out evenly, like we'll do 19 and 6, right? If we divide these two, we know that 6 goes into 18, or it goes into 19 3 times, right? And we get a 1 here. If we wrote this in quotient plus remainder over divisor form, right, we have that the quotient is 3, and then our remainder is 1, and our divisor, the thing that we're dividing by, is 6. Okay, and this is how many times 6 goes into 19, right? And hopefully, you can just plug that into a calculator, and that ends up being true, right? 1/6 is, I can't remember the exact number, but it's like, it's half of 1/3, so 1/3 is 0.333. You just end up dividing that by 2 and you get 1/6. Okay, and so you'll see that the answer is this, and so that's why quotient over remainder, or quotient plus remainder over divisor, that's why that's so nice, because it's your actual answer. Anyways, let's move on here and let's do some long division with polynomials. Okay, so all you have to do long division, right? We'll say, how many times does this term go into this term, right? We want to look at the first term on each. So how many times does x go into 2x squared? In other words, how many times, or x times what will give me 2x squared? Well, 2x, right? And so we'll write down a 2x here, right? And say, well, okay, we have a x plus 6 times a 2x. That will give us 2x squared plus 6 times 2x is going to be 12x, right? And so we just have a 2x squared plus 12x, and we're going to subtract that piece. Okay, and so in subtracting that piece, we get that 2x squared minus 2x squared is 0, and then a 15x squared minus a 12x squared is going to be 3x. Okay, and now let's do this whole process again. All right, let's make it quick. Let's do it again. We want to see, okay, x plus, and no, sorry, we'll bring down the 20 as well. We want to see x plus 6, right? The first term here, how many times does x go into the first term here? 3x. Well, again, that's just asking x times what equals 3x. And we know that that would just be 3. So we're going to put a plus 3 here. We're going to multiply x plus 6. We'll multiply the whole thing by 3. Okay? And we're just going to, and the reason why we ignore the plus 6 here is because we want to get rid of this largest term like we did here, right? If we ignored the, when we ignore the 6, we're able to do that, right, pretty easily. Okay, otherwise it'd be a nightmare trying to figure this out on our own with the plus 6 in. But when we're subtracting, we need to actually have that plus 6 in, because then we would just be fudging numbers. Okay, and so here we get 3x plus 18, right? And so we have a 3x plus 18, and we're just going to be subtracting. Oops, that's a highlighter. We'll be subtracting this whole thing. Okay, so when we do that, 3x minus 3x is 0. 20 minus a 18 is going to give you plus 2. Okay, and so now we have everything we need, right? Our quotient is up here, our remainder is right here, and our divisor is right here. Okay, so we get that, we get 2x plus 3 plus our remainder, 2, over our divisor, x plus 6. Okay, and that is it for that problem. Okay, so moving on to problem 37, let's talk about remainder theorem. Okay, we're going to use remainder theorem to show if x plus 1 is a factor of p of x equals x cubed minus 7x squared minus 11x minus 3. Okay, and I have the remainder theorem down below, but first off, let's make sure we understand what this question is asking. Okay, we want to see if x plus 1 is a factor of this. That means that, when we actually go through and factor this thing, right, we want to be able to write it as x plus 1 times some other stuff, right? And x plus 1 needs to be one of those factors. Well, if we, multiply these two, whatever these two things are together, we would get like some kind of quadratic, right? And so the idea is that if we divided x cubed minus 7x squared minus 11x minus 3, right? We divided that by x plus 1, we get this thing. We get this quadratic. Okay? But it would be nice if we could just, like, do a quicker way other than having to do this entire thing all the time, right? And so we have this remainder theorem that we can use. Okay? And we can figure out whether it's a factor of this or not. Because the idea is, right, this would be our quotient and our remainder would be 0, right? Because notice when we do this thing divided by this thing, it's not like x squared plus x plus 2 and that's your quotient and then you have plus some remainder over a divisor, right? You just get this thing because the remainder is 0. And so this, this piece just gets zeroed off. Okay? And so if x plus 1 is going to be a factor of this thing, if x plus 1 is going to be a factor of this thing, then our remainder is going to have to be 0, right? Because we want x plus 1 to go in evenly. Now so that's what we're asking for here. Let's get into what remainder theorem actually is, though. What remainder theorem tells us is that if we have some polynomial that we're dividing by some binomial, right, we can illustrate our answer, right, and this is quotient plus remainder over divisor form. Here's our quotient, right, that's regular. Here's our divisor. What's different is what our remainder actually is. That's why this is called remainder theorem. Remainder theorem states that your remainder in any of these problems, right, is going to be the same polynomial that you started with, right, that p, but now you're going to plug in a, right? You're going to plug in the opposite of, instead of minus a, right? So like for x plus 1, a is going to be negative 1, right? Because if you have x minus a, to get x plus 1 into that form where it has a minus sign here, you could write it as x minus a negative 1, right? And so there a would be negative 1. And that's why you have to flip the sign. Okay? So hopefully that makes sense. So a is going to be negative 1. And so to find the remainder of this really quick, we can just plug in a negative 1, right? We can just plug in p of negative 1 in this case. But I know that's a lot. Before we actually do that, let me just show you that remainder theorem works with our previous problem, right? Let's show that we get a 2 as our remainder when we divide out this piece. Okay, let's just show that quick. Well, remainder theorem says that if this is our dividend, right, and this is our divisor, our remainder will be this thing, right? We'll call that p of x when we plug in a, right? And a here is going to be negative 6, right? This is positive 6. We flip the sign, we get negative 6. Okay? And negative 6, when we plug that in, we get 2 times negative 6 squared plus 15 times negative 6 plus 20. Okay? And then that equals 2 times 36 plus, actually it'll be minus a 15 times 6. Well, we know that 15 times 4 is 60, and so 15 times 6 is 90. And then we get plus 20. And then this becomes 72 minus 90 plus 20. and that gives us 2. Okay, and so yeah, we can see that our remainder is just when we plug in, we plug in -6 for our dividend, right? Our dividend is p of x, right? When we plug in -6, we get our remainder, and so that's cool. It works, right? And remember, the 2 is our remainder right here. It's kind of interesting. So what we're gonna do now is we're going to plug in -1, right, for our p of x, right? We're going to play that into our p of x, and we're going to see if we get 0 here. And if we get 0, then we know that x plus 1 is a factor of p of x. Okay, so let's do that. Let's get a white marker here. And so let's go ahead and do p of x is x cubed minus 7x squared minus 11x minus 3, and we know for our a, we flip the sign and we get -1, right? That comes from here. And we plug in -1, we get a -1 cubed minus 7 times -1 squared minus 11 times -1 minus 3. Just plugging in a -1 everywhere we see an x, right? And when we do that, we get a -1 plus, no, it'll be -7, right? We have a -7 times -1 squared, that's 1. And so -7 is the answer for that part. And then -11 times -1 is 11, and then we get a -3. Okay, and so just combining all that, -1 minus 7 is -8, minus -1 minus 7 is -8, minus 3 is -11, plus 11 is going to give us 0. And so since this is true, we can say that x plus 1 is a factor of x cubed minus 7x squared minus 11x minus 3. Right? For the last time, I'll review quickly why that is, right? We want to divide that, if we want to factor this thing, we're going to divide it into x plus 1 and maybe some quadratic, right? And that quadratic that we're going to get when we do this long division is not going to be x squared plus 5x plus 2 plus 3 over x plus 2, right? This is that remainder over divisor from before. Our remainder is going to be 0, right? And actually, sorry, so this right here will be x plus 1. If we want to actually be real here, I mean, this isn't correct, what we have here. So I guess, yeah, I'm just kind of fudging numbers right now. But you get the whole thing, the fact that our remainder has to be 0 because this piece isn't included, right? You're just going to get something like this when you do the long division, since x plus 1 is a factor. Okay, and if you don't see that, try to do the long division yourself, and you'll see that you just get this piece and this piece. There's no fraction or anything like that. Okay, so hopefully that makes sense. I know I spent a lot of time on that. I just really want you to understand the idea with remainder theorem. So for problem 38 here, we want to use the remainder theorem to find the remainder when x squared minus 5x plus 3 is divided by x minus 8. Okay, the remainder theorem is stated below here. We've used it, right? And let's just figure out what our a is, right? Let's figure out this remainder by plugging in a. We flip the sign here, we get that a equals 8, right? And we can just plug that in, right? P of 8 is going to equal this thing with 8 plugged in for x. 8 squared minus 5 times 8 plus 3. That equals 16. No, not 16. I made this mistake when I was scripting the notes. 8 squared is not 16, it's 64. All right, minus 5 times 8 is 40, and then we get plus 3. And so that gives us 27, right? 64 minus 40 is 24, plus 3 is 27. And so when we do this long division, our remainder will be 27. Okay, so that's our answer. All right, so that's going to do it for part 2 of Algebra 2 Final Review. I really hope this video helped. If it did, definitely subscribe. And I also have my Patreon, which you can, go support me on, everything like that. For if you're taking future math classes, just know that I will have a pre-calculus course, a calc course, all that stuff that you'll need. That'll be out soon. So it'll also be down in the description if you want to go check that out. But anyways, yeah, thanks for watching, and I'll see you soon.